This is Aaron Cohn's first lecture, and a few minutes into the lecture, Aaron reviews his personal history both before, during, and after his NASA career, so I won't give any more information about him here except to say that he was a wonderful man and a superb systems engineer. Aaron could be tough as a program manager, and many engineers were certainly frustrated by his continuously having to reject their demands for changes in the systems that would increase cost or delay the schedule. But personally, everyone liked and respected him. I was present at his NASA retirement party, and the warmth and affection felt for him by all the employees at NASA's Johnson Space Center was really apparent. Aaron was a personal friend, and without him, this course would not have been created. Aaron died in 2010, and we all miss him, but we're lucky to have him on video, and I hope you're going to learn a lot from him, both about the space shuttle in particular, and about general principles of systems engineering, of which he was a master. Let me now just make a few comments by way of explaining some of the things that Aaron refers to. At the beginning of his lecture, Aaron talks about students working on the design of new spacecraft. Redesigning the space shuttle using 21st century technology was part of the assignment to students taking the course for credit back in 2005. In general, I've tried to edit out references to this assignment, but I leave this initial mention in just as a reminder to our online students that hearing lectures is only part of the education process. Ultimately, you have to use the lecture material to do projects and solve actual problems in order to cement your knowledge. You won't be doing a design project as part of this online course, but I hope that at least some of you engineering students out there will be able to make use of what you learn here in your engineering careers. Aaron mentions early work with the MIT Instrumentation Lab, and then he refers to the Draper Lab. Charles Stark Draper, or Doc Draper as he was always referred to, became famous for his work in the development of inertial navigation systems. He was head of MIT's Aeronautics and Astronautics department, and he created the Instrumentation Lab, which at that time was part of our department. The first contract that NASA made as part of the Apollo program was with the Instrumentation Lab to develop the computer and inertial guidance systems for Apollo. In the early 1970s, the Instrumentation Lab became an independent, non-profit entity renamed as the Draper Lab. Draper formally separated from MIT, although we still have close ties, and many faculty and students in the Aero-Astro department at MIT work closely with Draper scientists and engineers. At the very end of Aaron's lecture, we had to edit out some irrelevant comments, so the lecture as presented here ends quite abruptly with a few comments by Aaron on various aspects of systems engineering as they applied to the design of the space shuttle. So, here's Aaron Cohn's first lecture about the early development of the space shuttle.
You're going to have a very unique opportunity. You're going to have people speak, lecture you on the various shuttle subsystems in quite a bit of detail. You'll have some people that will be very, very positive about the shuttle, that think it's a great design, a great operation. You'll have others that will not think it's so good. And you'll have some that will give you just a detailed technical approach of what happened. I think what I would like to suggest to you, for your good and for the good of the future students, future designers, that you ought to come up with your own decision. Was it the right design? Was it the correct design? Should it have been done differently? And if so, why? And how would you do it? And I think that'll be good for you after you get to work on when you go to work on future projects. It'll also be good, I think, for NASA, something we could turn over to NASA. So I think it's a very valuable thing to do. So I would suggest you do that as you go through the course. And I will be happy, very happy, to talk to you about any of your ideas that you have through the internet, through emails, or in personal discussions. So, and you might want to do this later on as the semester develops. A little bit what I'm going to say today really starts off from where Dale Myers, your previous speaker, left off, and it gets a little bit more detail. So it's going to, as this course develops, you're going to get more and more and more detail. But let me start off again, just very much like Dale did, and talk about the shuttle history. In 1952, fully reusable launch vehicles, the concept was discussed. People were interested in that. In 1962, fully reusable vehicles were seriously considered. The Air Force studied Project Dinosaur, which was canceled in 1969. In 1969, NASA adopted the idea of a fully reusable spaceship. I became the Orbiter project manager for NASA in August of 1972. And at that time, I also was manager of the Systems Engineering Organization for the first 2 years. So I had the total, you might say, the total system at that time and the Orbiter in 1972. Yes?
Could you tell us a little bit about your background that got you to that position?
Well, my background was that, yes, I started off at, I graduated from Texas A&M University in 1952 and went to the Army, went to Korea. And then when I came back, I went to work for RCA. And I went to work and worked on the microwave tubes, the microwave oven. In fact, when I told my wife what I was working on, I said, I'm working on a microwave oven. That was in 1954. That was a long time ago. How many people have microwave ovens today? Everybody does. Well, 1954, 1955, when they came out, they were about $3,000 a piece. I was working on one. I told my wife, and we've been married a long time, I told my wife that I was working on something called a microwave oven, and you're going to be able to cook a roast in a couple of minutes, and a potato in a couple of minutes. And she looked at me and she said, that'll never sell. So, anyways, that's what I worked on. Then I worked for General Dynamics on the Atlas and Centaur, and then in 1962, I went to the Johnson Space Center and worked very closely on the Apollo program. I worked very closely with the MIT Instrumentation Lab, now the Draper Labs, on the Guidance, Navigation, and Control System. I became head of systems engineering in Apollo, then manager of the Command and Service Module in Apollo. Then I became the, in August '72, I became the manager of the Space Shuttle Orbiter. Then I became director of research and engineering at Johnson Space Center. And then I became director of the Johnson Space Center. And then I became, for a while, I was acting deputy administrator in Washington. And then I retired and went to Texas A&M to teach. And then Jeff asked me to come do this, and I'm very happy to be here.
Thank you.
Okay.
Actually, one thing that you mentioned reminds me of something which, you know, not to divert the lecture today,
That's
but
right.
the fact that there was specifically a systems engineering group at the center, which was separate from the project offices.
That's right.
Is something which is probably worth talking about at some point.
Well, let me just make a mention of that. In Apollo, when we were in Apollo, we sat around the table for many days and months trying to figure out how you define systems engineering. We really didn't know what systems engineering was. In fact, today, I'm not sure you'll get a clear definition of what it is. I want to give you some examples as we go through the lecture. I'm going to give you some examples of what I think it is and how it was used. Something that's very key in any design, and something you really need to pursue whenever you do a design project, is understand the requirements. Because if you don't understand the requirements, you made a very good product that's useless. So you got to understand what your customer wants, the top level requirements. One thing that was handed down to us, it was supposed to be fully reusable. That was one requirement. 14-day turnaround time. You were supposed to be able to turn the shuttle around in 14 days. Deploy and retrieve payloads. You have to deploy a payload and you have to retrieve a payload. Design and development and test is estimated to be $5.1 billion in 1971 dollars. Dale Myers didn't tell you the whole story, but one of the reasons that Dale Myers and I are such good friends, he was associate administrator of manned spaceflight. I was the Orbiter project manager, and they being headquarters is always there to help, actually took away 2 years of inflation. If they had given us those 2 years of inflation, we would have met the $5.1 billion in '71 dollars. And Dale fought for that, but lost. The original, here's where we missed it. The original cost per flight for 65,000 pounds was $10.5 million per flight in 1971 dollars, but for a flight rate of 60 flights per year. When I told my wife I was doing that, and she's been around the space program a long time, said, you never agreed to that, did you? But 60 flights per year is pretty hard to do. But that's what we came up with at the time. Now, Dale mentioned the Air Force requirements, but here was the Phase A studies. The Phase A studies were conducted to determine the basic requirements and their effects on design in 1969. The principal issues were the size and weight of the payload, the cross range of the orbiter, and what kind of heat material were you going to use. You got to recognize that the heat resistance, we're going to use heat resistant structure or reusable insulating material. You got to recognize that our background was a Mercury, Gemini, Apollo, and they all used an ablative material. And ablative material cannot be reused because basically the surface changes. You had to have some kind of insulating material so the surface did not change. Okay, so now the shuttle studies, the principal issues in the shuttle studies, now we're starting to get a little bit more technical and a little more details, is should the reaction control system, now the reaction control system is basically a propulsion system that controls the vehicle about its center of gravity. It's for attitude control, basically. So basically, should the reaction control system be liquid oxygen, liquid hydrogen, or should you use a hypergolic system, where it's a storable type system? That was a big issue at the time.
Everybody here know what hypergolic fuel is? Let's talk about it a little bit.
Well, hypergolic fuel is a fuel that actually, like hydrazine, it actually does not need it's actually got an oxidizer and a propellant in the same fuel. Now, the other one was a fly-by-wire flight control system. That was a big issue. Do we have a fly-by-wire flight control system? And now everything has a fly-by-wire. All the military jets have fly-by-wire. But basically, was it going to be a digital control, computer control system, or were we going to have cables fly the machine? That was a big issue, a very big issue at the time. Wind tunnel test determined wing size and configuration. That is a very difficult thing to do, but this is starting to get into what you might say is systems engineering. This is starting to get into what you might say is systems engineering. Air-breathing engines were considered for flyback and later determined to be too heavy. And some shuttle studies that still had to be done was the entry techniques, landing speed, what type of landing speed were we going to have, and the approach pattern. So these were some things that had to be understood during the studies. The Phase B studies, were performed in mid-1970s to determine the preliminary design. The results showed a fully recoverable orbiter, disposable fuel tank, parachute recoverable solid rocket boosters, high-performance hydrogen-oxygen engines placed in the orbiter to be recovered. This was all systems engineering that led up to the design. So you have systems engineering in various phases of the program. And usually systems engineering composes of an interdisciplinary team that has been given some assumptions, some constraints. They have some top-level requirements. They do an iterative process with some tools, such as computer tools for calculation of loads and flight mechanics, and they come up with an iteration of what the design is going to be. So that's basically how it was done. Now, that was sort of like the ground rules. Some of the things that came out of it, once we started putting the total system together, we showed that the fully reusable with a flyback booster was greater than $5.1 billion. So that was thrown out. Now, there is a question, and that's what I asked Dale. Should we have said, hey, we need money to really have a flyback booster? But they gave us a constraint of $5.1 billion in 1970 dollars, and it didn't make it. And I showed you many configurations were studied, and the turnaround time of 14 days dictated a landing with a winged vehicle on a runway. You weren't going to be able to land this in the water or with parachutes. You were going to have to land it on a runway so you could quickly turn it around in 14 days. The payload deployment and retrieval requirement determined the location of the orbiter on the launch configuration. Because if you look at that large payload bay, it'd be very difficult to put that on top of the vehicle. Now you're getting to look at what the design is starting to look like. This is the agency commitment in March of 1972. In May of 1972, you had the North American proposal, and then I became Arbiter Project Manager in August of 1972. We did a study, and PRR is the Preliminary Requirements Review. But that was the configuration. We made some changes, and the production commitment was made in May of 1973. This chart is not, it's sort of a gee whiz chart at one point in time, which showed the $1971 cost per flight for the Thor, the Atlas, the Titan 3C, the Saturn 1B, and the shuttle, and that's payload to orbit. So you can see that the thing that was really missed in the shuttle was the $10.5 million cost per flight. Okay, here's some of the major decisions. We were going to go with a hydrogen oxygen main engine. This size, now that's one of the system problems you have to decide. Once you decide what kind of propellant, what kind of engine you're going to use, that basically sizes the external, the tankage. And I'll show you that on another chart. But this, as I said, this size, the liquid oxygen hydrogen tanks, which is not reusable. I'll make that point to you a little later on. But once you decide what kind of engine you're going to use, that sizes the tank because of the using the equations of motion. I'll get your question. You can figure out how much propellant you need. You get the density of the propellant, and now you know what size tank you're going to use. Solid rocket boosters provide the additional propulsion required to get the orbiter in orbit, and the solid rocket boosters were designed to be recoverable and reused. So those were some of the system studies that led to the configuration. Yes, sir.
Aaron, at that period, was there any discussion of the environmental impact of solids being used at 60 flights a year?
Yes, there was. There was quite a bit. There was quite a bit. I don't recall the details, but I do know there was a lot of work going on that many solids being used. And I guess we basically put that to rest, but there was a lot. I don't know the details of it. In fact, that might be a good question. If you're not here, we'll ask J.R. Thompson, because J.R. should know that. I mean,
when I met with some of the Russians who worked on the Buran, which was the Russian copy of the shuttle.
Right.
One of the big changes was that they said, how could the Americans have used solids?
70 flights. It was studied and actually put to bed, or put to rest, should I say. I don't know the details, but it's a very good question. That's something I think they're going to be various speakers, as I said, and JR should have that answer. Solid was recoverable and reused. Well, some of the things I've said before, the arbiter decisions, the arbiter entry cross range required delta wings. To go 1,100 nautical miles cross range, you needed delta wings. Deletion of the air-breathing engines for moving orbiter required the Boeing 747 to carry the orbiter. Let me tell you that story. All of you are very familiar now that when we landed at Edwards Air Force Base, we put the orbiter on top of the 747 and we ferry it back, fly it back to Kennedy. Well, I was the orbiter project manager, and I became orbiter project manager in August of '72, and I was having all sorts of problems. The first thing they did to me was they cut my budget in half. The OMB cut my budget in half. So that was the first thing that happened. And then I just had a lot of problems. So, but I had worked on the Apollo program. I had a lot of friends in the organization, although I was orbiter project manager. 3 of my friends came into the office one afternoon, I forgot, maybe 2 or 3 months after we started, and said, Aaron, we got a great idea. I said, what's that? He said, we can put the orbiter on top of a 747 or a DC-10 and ferry it and fly it back to Kennedy from Edwards Air Force Base. We may have to make 1 or 2 stops, ferry back. I looked at him for a moment. I said, that is absolutely the dumbest idea I've heard in my life. And I basically threw the people out of my office, and they were my friends. Well, these people will not take no for an answer. Happened to be they had another very good quality. They were all world-class model airplane builders. I mean, these guys had won competition all over the world, 3 of them. So they came back about 10 days later, said, you know, I don't know how many you've seen the Johnson Space Center, but we have a lot of acreage out there, Texas. And they said, come out, we want to show you something. They had built a radio-controlled model of the 747 and an orbiter, and actually flew it for me and separated the orbiter from the 747. So that's how it got started. That's how, and so we eliminated the air-breathing engines. But I remember throwing them out of the office. 5-wire with a digital autopilot. Yes, sir.
Are you saying that if you had air-breathing engines, the orbiter itself would fly back?
Yeah, that's a good question. I missed that point. Let me explain to you. If you recall, that's exactly right. When the orbiter lands, you know, the landing gear, the nose gear is very short, so it's sitting there. What we had to do, you asked a very pertinent question, we had to actually replace the landing gear with a different landing gear that caused the orbiter to have an attitude like that. We put air breathing like this, so it wasn't like this, it was like this. We put air breathing engines on, and we took off, and we had to have 5 in-flight refuelings to get from California.
Strap-on
Yeah, and plus a different landing gear. And we took off horizontally, and 5 in-flight refuelings to get from California to Florida. So that's the real, and you really brought up a pertinent point that I left out. That's the reason why we changed it. Thank you very much. And of course, we went with the fly-by-wire with a digital autopilot. This was a very fundamental change. The astronauts at that time did not like this very much. Now, when you get all these new pilots in, they wouldn't know, what are you talking about, fly-by-wire? Why not have a fly-by-wire system? But they didn't like it at one time. But we went with the fly-by-wire with the digital autopilot. I'm going to talk a little bit more, even though you're going to have a special briefing on the guidance, navigation, control system. I'm going to talk a little bit more in detail about that because that happens to be my expertise. So I'm going to talk about that a little bit more detail. Yes, sir?
What does fly-by-wire mean?
It means that you actually have a computer actually controls the surfaces.
Okay.
Whereas in an airplane, in past airplanes, your stick actually had cables that controlled the surfaces. So you get a lot more performance out of it. I mean, okay?
It's a little bit confusing in the sense that a wire, you might don't think of it as a hard wire, which is like the old type of an airplanes where there was a cable.
Right.
So when you pulled on the stick, there was actually a cable which went back to the ailerons and the rudder and everything. And you know, as Professor Cohn says, everything now has a computer in the middle, and what you're really doing is flying the computer, and the computer then issues the commands to the hydraulic system. But that was, the shuttle, I guess, was the first
shuttle was the first
vehicle that really had that system.
That's right, exactly.
There were no commercial planes flying with that system.
Or military planes flying.
Yeah, I mean, they...
Yeah,
So it was, and you know, the real concern was safety and reliability.
That's right.
You know, suppose you have a computer problem, what are you going to do?
I'm going to talk about that in detail, but that's a good question. Any other questions? Those are very good questions. I appreciate it. Yes, sir.
Can you just explain cross-range again?
Cross-range, basically, you realize the orbiter is a glider, so to speak, a glider. Not much of a glider, but a glider. And it actually, downrange would be going in this direction. Cross-range would be out of plane, basically, out of plane direction. So you can actually maneuver out of plane.
We've got a nice globe here. I'm not going to carry it up to the front, and I don't have a piece of chalk either, but...
Here you go, Jeff. Jeff, there you are. Good. These are very good questions, by the way. Thank you very much.
Okay, so, you know, here's the U.S., roughly. So this was designed for the military requirements, okay? So they wanted to be able, for reconnaissance satellites, basically, you want to be in polar orbit because you're going around, let's say this is an orbit here, and then the Earth turns underneath it, and so you basically fly over all parts of the Earth. So that was the basic military requirement. They wanted to be able to launch out of Vandenberg on the west coast into a polar orbit. And because of security reasons, they I mean, you know, this sounds a little bit strange when we think back on it, but you wanted in a time of crisis, remember we were in the Cold War and everything, you wanted to be able to put a satellite up without necessarily giving the other side a chance to make all the radar measurements on the shuttle and everything and figure out right away where the satellite is. And also there might be hostilities, they may be, you know, the shuttle was a strategic asset. So basically they wanted the shuttle to be able to land the very next orbit. Well, all right, you take off from California, you fly over the pole, you deploy your satellite, and by the way, we have never ever, with all the satellites we've deployed, we've never deployed a satellite on the first orbit. That would be an incredible feat, but that was the requirement. So you fly over the pole, you come back around, now you're ready to land in California, but during that time, the Earth has turned by 1,000 miles. Okay, you know, it's 24,000 mile circumference and 24 hours, and actually 1,500 miles because an orbit is 90 minutes, 1.5 hours. So your orbit now would put you right over the Pacific Ocean. If you just burn your engines, slow down, and come down through the atmosphere, that's where you're going to land. So instead, as you're flying through the atmosphere, you basically have to come down banked on your side, and so essentially you're generating a lift vector, and instead of turning your lift vector up, you turn your lift vector to the side, and that pushes you over. And delta wings can generate a higher lift vector than the straight wings, and that was the determining factor.